And so what we need to do here is, can you guys even read that? Yeah? No? Okay. Okay. So the question was, calculate the ionization energy of a 2p electron, which is nitrogen. Okay, and there's my pen. Okay. And so the first thing we need to do is figure out the electron configuration for that element. Okay? And so we look up the periodic table, and we just go along the periodic table. So we have our 1s orbital, that's H and He, right? We're past that, so those are full. So 1s2, okay? And then we go along, and we go, well, we're period 2 now, right? So N is period 2, nitrogen. And so we have a 2s, and that has 2 electrons because we're past that, right? We're full. And then we go along to the next one, and we go, how many into the third period are we? I'm sorry, second period are we? You're 3, yeah. Dyslexia, huh? Gave you the answer. And so in the valence shell, we have 2 electrons in the S, 3 in the P, right? So in that valence shell, we have 5. Okay? Okay. And so we can ignore the core electrons because whenever we're talking about energetics, ionization energies, we're not going to blast electrons out of the middle, right? We're going to blast them off of the surface, right? Which is the valence electrons, the outermost shell. So those 5 electrons in the outermost shell, those are the ones that could get blasted out of here, okay? Okay, and so what we need to do then is figure out the energy for those. Now, so the subshell, which is the shells below the valence shell, the core electrons, those ones are going to be the same for both of these, right? They're not going to change at all. We just have to worry about valence electrons in this problem. Okay. Okay. So the thing we have to calculate now is we have to get the nuclear charge that's felt by those valence electrons, because that's the power of the magnet that's holding these, right? And so how we figure out the ionization energy is how much energy is it going to take to pull this electron away from the magnet holding it, right? And that is dependent on 2 things. The nuclear charge and how much it's shielded, right? And the sum of those things is the effective nuclear charge. Did I lose anybody so far? No? Okay, so we're going to get effective nuclear charge for these 2 items, okay? Okay, so this right here is the formula to do that. Now, note that in these 2 formulas, the core electron portion of this formula is the exact same. There's no difference there, okay? Okay. And so what we have first is we have Z, which is just the number, right? So we look up at nitrogen, and what's that number for nitrogen? 7, yeah. And so that would be your normal nuclear charge, right? If you had no electrons around it, that would be the amount of protons pulling, okay? But we have electrons that are going to be shielding that and causing that to be a weaker number, don't we? Okay. And so that's this part right here. Can you see that, the 7 there? Okay. Every other term is going to be subtracting off of that, isn't it? Okay. And reducing that effective nuclear charge. So there's 2 portions to this next part. You see this portion right here and here. Those are the 2 portions that we have to account for. The first portion is the electrons next to it in the valence shell. Those have different numbers, right? Because one of them we're going to be blasting the electrons off, and so we'll lose an electron, right? The other one, we have all the electrons, okay? And so that's the difference right there, is right here we have 4 electrons. Here we have the 3 electrons remaining, okay? Okay. So those would be the other electrons shielding it. Can anybody tell me why it's not 5 and 4? Mm-hmm.
The 2s2 is included in the 2 parentheses 0.85.
Okay, so let me go ahead and talk about that real quick. So the 2 times 0.85, okay? Okay, so in terms of shielding our ability to look at each other, right? The person next to you doesn't do a lot, do they? A little bit. Like if I got far enough over, it'd be an issue, right? His computer. Okay. But Blaze, you're the core electron to me, aren't you? Yeah. So these would be our energy levels right here, right? And so you two are my core electrons, aren't you? Yeah. And you four are my valence electrons, aren't you? Okay. And so who shields the most in terms of blocking me from you? Yeah, of course, the core electrons, right? And so we have two core electrons in this system. They have a effect that's 0.85. Okay. And so that's where the 2.85, 2 times 0.85 comes from. Is those are your core electrons. They're the same for both systems, and so you have the same system 2 times 0.85. Okay?
We still calculate them because they're still the valence, even though they're not the outermost valence orbital.
They're the most effective shielding.
Okay.
So what we're calculating right now is how much pull your core, your nucleus, exhibits on an electron right now. And then we're taking the difference between them. Okay? And so, for example, these right here actually are the largest contributor is right here. This one is the largest contributor in terms of shielding. How much your effective nuclear charge goes down. Is that making sense so far? Okay. Okay. So the other part is this right here is your nucleus right there. These are your, okay, I'm going to put nuke. Okay. Or Z. You guys okay if I just do Z like that? Okay. Everybody's okay with that? Okay. These are core, right? Okay. And this term in the middle is actually your valence electrons, isn't it? But it's your valence shielding. Okay? Okay. Now, when you're talking about shielding, okay, so I have a football game happening, right? Quarterback passes a ball to somebody catching the ball. Okay, I'm not going to go into the terminology super deep. I don't know how much you guys actually watch football. But, so, in terms of shielding, if you have two people covering, do you count 3 because there's 3 people there, or do you count 2 people covering? 2 people covering, right? And so our numbers are, there are 5 valence electrons, right? The number of valence electrons that are shielding one of those electrons would be then 4, right? The 5th one is the one getting shielded, right? Is everybody okay with that? Okay. And this other state right here, that's the star, the excited state, that's the one that lost the electron. We're going to be taking that difference there. Okay? That's the energy difference for losing it. And so that one has lost the electron and only has 3 valence electrons shielding the 4th electron. Is that making sense? Okay. Okay. Did I lose anybody there? No? Mm-hmm.
Where are we getting the 0.35 from?
The 0.35 is actually a shielding factor.
Oh.
It's how well coverage happens. So if it was like our example with the football game, okay? The person that is in front shields the ball from the catcher better, right? The person to the side doesn't do as good of a job covering, okay? And so they only get a 0.35 factor. The person in front gets a 0.85 factor, right?
Is that stuff we should just memorize, or would that be given to us?
That'd be given. It's a constant.
Okay.
Yeah. And in fact, it's right ahead of this problem in terms of your chapter. So there's literally a little like text table thing right there. Okay, so this is a overall shielding factor that you would do in all these calculations. Yeah, I don't have any desire for you to sit down and memorize this crap. So, yeah. Okay. Now, what we're going to do then is we're just going to take, remember the nuclear charge minus the ones in the same valence shell times their 0.35 minus the one in the core shell, which is then multiplied by 0.85, right? Okay. The numbers we're going to get here is 3.9 and 4.25 right there. Okay? Okay. So once we have how powerful the magnets are on work on these electrons, what the effective nuclear charges are, we can go ahead and get this formula right here, okay? Okay. So in this case, we can actually make this formula a little bit less long, okay? So this formula is in your book. It's the ionization energy, okay? And it's a constant right there times the valence electrons times the effective nuclear charge, okay, over these twos. And those numbers are then squared. Okay. Can everybody read that okay? Okay. Now, notice that it is an absolute value, so even if you screw up a little bit in this, it'll fix it. Okay. Okay. Now, once we plug these values in, we're going to get 3.9 less effective nuclear charge for the 5, right? And then 4.25 for the 4 valence electron 1, which is where we blast an electron off. And then we go ahead and solve for this, and we're going to get out a 12.9 electron volt. Okay. Anybody have any questions about that? Note it's essentially the difference between how well it holds on to those electrons. Can you kind of see that? Those are your big terms. And then a constant factor to correct it into EV. Okay. All right. Note that, yes, this is not perfect. It's actually a little bit off from the actual value. Yeah. One of the reasons I actually asked this is, did anybody notice that this is the number we used on that other problem that we did the example of? Yeah. Yeah, we plugged this in. Okay. Anybody have any questions? No? Okay. Let's see. It was on 32. This one. Okay, so last time we left off, we were talking about the core electrons when we get large atoms. Do they exhibit the same mass as outer electrons or electrons in smaller atoms?
They shouldn't they have varying electron masses?
They don't. They don't. And that's because of the theory of relativity. Okay? So you guys have always seen E equals mc squared, right? That's always what you've seen. Remember, there is actually a plus kinetic energy part, okay? But that, has a mass term in it, so it's not much of an issue. Okay, cool. But if we start actually looking at that, what we see is that that's only for when you're not going anything close to the speed of light, okay? As you get closer and closer to the speed of light, your energy goes up exponentially, okay? If we were hit by something that was going the speed of light and had any real mass to it, like if we were hit, if the planet was hit by like a small car going the speed of light, it would obliterate the planet, okay? That's not normally what you see, is it? Like, I hit myself with this. It don't really matter how fast I throw it. I'm not going to get obliterated, right? Okay. So what ends up happening is you start getting closer and closer to the speed of light, your mass actually increases. And this is because in that equation, E is directly proportional to mass, isn't it? Okay. And so when you have electrons that are core electrons that are very close to the nucleus, and something that has a lot of protons, so a lot of pull, you actually start accelerating these electrons fast enough that they end up coming into like actual real fractions of the speed of light. Okay, 0.2s, 0.5s, that sort of stuff. Okay, and then that means that their mass, not a huge amount, but their mass is larger than it would normally be. Okay. And so they effectively actually have greater mass. They get pulled in closer to the nucleus than they normally would be. And so that changes that entire dynamic of what the core electrons take up, how close to the nucleus they would be. Their masses are a little higher, okay? Because they're having a tremendous amount of attraction being applied to them, right? In comparison, remember that we're talking something going from, look at your periodic table real quick, and hydrogen is 1 electron, right? Francium exhibits 87 times the force. And that would only be a linear force increase. It actually is a bit worse than that, because it's not a linear increase as you increase attractions, right? So francium exhibits a tremendous amount more force on its electrons than hydrogen that are in that first orbital, don't they? Okay? And so the acceleration of those things is tremendous. They're zipping along. All right. We never see them. We never interact with them because we have a bunch of layers outside to go through. And they're so tightly held, right? But they have a tremendous amount of force on them. So what happens here, the overall effect of this, is that it's going to be to lower the energies of your S and P electrons while raising the energies of your D and F electrons. This is one of the reasons why we get further and further out in terms of expressing D and F electrons. So you look down and like the F electrons, they don't exhibit and show up until all the way down the 6th period. See that? Whereas the D were only trailing by 1 period, right? And so those core electrons reduce in energy. The outer electrons actually go up for the DNFs, okay, in energy. And so this is actually what you start seeing. It's not a massive amount for most of these, but it's very noticeable, okay? So normally here you would see a 5D orbital here, and then this right here would be a 6s. Okay, that's what you would have for a 0 order energy. You have no real relativistic effect. When we actually start adding in the relativistic effect and the fact that these electrons that are in those s orbitals for these start experiencing greater pull, we actually start seeing that the 5D here goes up and the 6s goes down. Well, if you bring those pretty close together, what ends up happening? Yeah, you can have things like pairing electrons all of a sudden causes stuff to want to go up into the other orbital, right? Yeah. And so you can start getting some interesting situations. Okay. Notice also the 6p goes down just a little. Just a little, right? But the 6s and the 5d is where this really exhibits a huge impact. Okay. So this right here is going to be the inert pair effect. So elements that immediately follow the 4D and 5D transition series. So if we look at the transition series, those are the transition metals in the middle here. And this is going to be the 4D and 5D. What periods are those, by the way? So d orbitals trail by 1, right? Yeah. Yeah, so just add 1 to these numbers, and that'd be your period. So period 5, period 6, right? So these are going to have considerably less reactive than their group properties might predict. They're also going to prefer oxidation states that tend to be 2 lower than the usual group valence. And so you can actually see kind of interesting effects here as you start looking at these. If you look at these, anybody recognize W? Now, you don't see metal versions of molybdenum and chromium, do you? But tungsten, we see metal versions of all the time, right? That's a really, really durable metal, in fact, right? So you actually knew this already, didn't you? It was the inert pair effect, wasn't it? Yeah. You just didn't realize it, okay? Because you'd already seen these things like tungsten carbide and stuff like that. Okay? Okay, so again, those are going to be less reactive than their group would otherwise indicate. The lighter elements like boron, aluminum, gallium will take only a 3 plus oxidation state, which is what their group number would predict. That's that 3A up there, right? And so they typically 3 plus oxidation states. Okay. Normally those things have predictable oxidation states, don't they? But when we start going down more, what we see is that the heavier ones have 2 oxidation states. They can be a 3 plus, they can be a 1 plus. Why is that? Well, you have orbitals that are fairly close here, right? So there's not this huge energetic drive for only one oxidation state. You could have multiple oxidation states here that are fairly close in stability, right? Okay. So these are those reasons for the different transition states that you were seeing on the lower periodic table back in Gen Chem. Okay? That always been. You just didn't know it. Right? Again, group 14 elements, you can see the same thing. This is the one that's really like drives people nuts because group 14 or group 4A, carbon, right? Super predictive, carbon, silicon, germanium, cool. Typically loses 4 electrons, right, to something else. And so carbon especially, very predictable, right? We go lower, though, and we start going tin and lead, and all of a sudden these start acting like transition metals, don't they? Okay? And again, this is that same effect you're seeing of the orbitals coming closer, so you have 2 different charge states you could be in, right? The difference is 2 electrons. Why would it be 2 electron differences? How many electrons go in orbital? 2. So we have 2 orbitals that we can choose to be in. If we have both of these filled up, we would have 4 electrons there, right? Okay. We lose one of the orbitals, we'd have 2 electrons, right? So 2 electron differences typically are very common in these things because you're seeing these orbitals come very close together, and so you have pretty close stabilities. Okay.
Whenever I'm picturing an orbital,
Mm-hmm.
like every time I think of it, I think of just like a circle around the nucleus. Like, what should I be picturing as far as an orbital?
Okay, so the example I usually use is desks in a room. Okay? And so your shells are actually rooms, right? And then you fill them in with these desks. And so right now, and the desks, this works better when I have desks that are 2-person desks. But think of the desks as
2 electrons, right?
yeah. And so, for example, this room right here has this shape because there's another orbital in there that's blocking this one, right? This would be like a P and a D, right? And when we arrange the electrons within this, well, we're going to end up with the shape. That would be the electromagnetic field, the place you could have them, excluding the other stuff. Is that making sense? And so the exact orbital shapes are kind of not super important. Like I can usually picture the S and P's okay because, yeah. But in the hybrid orbitals, I'm usually okay with. I sort of don't even think about the D and F's and try to picture them in my head unless I have them in front of me. Because they start getting complex because you have those other shapes that exclude, right? And it's not really usually worth having that in your head. But in general, remember there are places you can fill electrons in. So they're like arranging these desks in these weirdly shaped rooms. Does that make more sense?
Yeah.
Okay.
Either like each room can hold a certain amount of, 2-person desks.
Exactly.
Like in the S.
Depending on how far away from it is.
Yeah.
Yeah. Like downstairs, because it has all the nucleus of the university. You don't have a lot of space, right?
Right.
And so there's fairly little room you can put people in desks in, right? And then we get to the next floor, and there's more, functions of the university are still there, but less, right? So we have more room to fit desks. And then we arrange them in these weird room shapes to use up that room, right? Mm-hmm.
I might be misremembering, but doesn't it have 5 orbitals?
Yes.
Okay.
Yeah.
instead of like putting into either D.
So what's ending up happening is your orbitals are blending into close proximity to each other. Actually, these ones we were just talking about were actually p orbitals that we're starting to fill in. But the ions are going to be losing the p orbitals. So what we're looking at here is actually the losing the p orbitals. And then what we'd be doing is we'd be losing electrons from the next one, which would actually end up being the s orbitals in this case. And that's why you end up with the 2, is because the s orbitals only have 2. And then the next energetically favorable would be the d orbitals, which have 5d orbitals, 10 electrons in them. But do keep in mind that you can end up with some jumping around, typically in the pairing sections. Okay, so 5 and 10 is where you typically see this weird behaviors, or the one right before it as well. Because the pairing, when you pair them, that jumps in energy, right? And so you can actually start seeing situations where you have like 4, and then the next one goes into here instead, because you're just the perfect energy difference. Okay?
Shouldn't they like repel each other though? I know you're saying the orbitals get closer and closer, but the closer they get, shouldn't they repel each other and increase the energy? Because you know, 2 electrons,
Yeah.
they're 2 negatively charged particles. So
Yeah, that's what they're doing. That's why the d orbitals and the f orbitals don't get used immediately. Is because you're packing in more and more rooms, right? More and more desks. It's actually, the desk analogy is really good, because if I packed in like twice the number of desks suddenly, you guys would not use some of the rows, right? You just wouldn't fill them in because you won't want to sit there. In fact, you guys are doing it right now, aren't you? Like, you're not all in one. Technically, this would be the optimal desks, right? Yeah, too close. You know, I actually had a lecture where I didn't have a podium. The room only had desks, and I used to sit down at one desk, and somebody sat down directly opposite me at the desk, like a romantic night at the bar. It was different. It's too close. Like, this is too close. No, that's imagine sharing the same desk. It's like, yep. Yeah. Anyways, did that make sense? That's actually why we don't see these d and f orbitals, and those actually get moved back, is because it ends up boosting their energy up. Like, this should have been filled in back in the 5s, right? That's where it was actually available. And that would have been the same spatial dimension area. Does that make sense? Yeah. Okay. Yeah, and the 2 electron difference is because the s right here. The s orbitals only have 2 electrons. Okay. Anybody have any questions about that? Okay, fantastic. Keep in mind that one of the things that also happens is, as we pull down these energy levels here, that, the first oxidations are not much of a problem. We boost up this one, but we also cause a situation where having these very large oxidation numbers starts becoming very difficult to do. Okay? So that's why things like chromium has a hexachromium version, right? You guys all know hexachromium? No? Ooh, I have a chemical leak for you. So, anybody ever heard of Erin Brockovich? No? Yeah? Okay, if you get a chance, there's a movie about her. Really good actors and actresses are played in it. It's based on a true story, and the story actually happened. So Erin Brockovich was trying to be a paralegal and ended up being a paralegal. Okay? And they got contacted by this small town of people that were all developing various forms of cancers and diseases. About 400 of them developed various forms of cancers and diseases. I believe 100 and some of them died from them. Okay? And They had no idea why, couldn't figure it out. And so the company in the town had leaked hexachromium into their water and then told them that, brought them all together 20 years previously when they leaked the compound in the water. The company knew they leaked hexachromium in the water. There were internal documentations. They knew the effect of hexachromium on people. They told them that we leaked chromium 3 plus into your water. Chromium 3 plus is in supplements. You take it, you need it in your diet. There's no negative health consequences to chromium 3 plus. And so the people didn't sue them, of course, because, hey, it's chromium 3 plus. No problem, right? It was chromium 6 plus. Chromium 6 plus is incredibly toxic. If you go to Tamil Nadu, you'll see no life at all for miles around because chromium 6 plus is leached into the soil. It will cause multiple different types of myelomas, cancers, lymphomas, just tremendous number of diseases. So it's actually kind of difficult to pin down if you're just looking at the end results. It is a heavy metal. It goes nowhere. Okay? Like poisoning somebody with carbon compounds, they break down. Okay? Poisoning somebody with heavy metals or a place with heavy metals, that doesn't recover. That just stays poisoned. Okay? So these people caused hundreds of deaths, this corporation. They finally figured out that it was chromium 6 plus, sued them in a class action lawsuit. They won that. It helped the victims a little bit. A little interesting side note, the lawyer that worked on that actually, the lawyer for Aaron Brockovich's paralegal, that guy actually later on, he took that pro bono actually, and so he was a hero. Later on, it had been found out that he actually had been stealing from clients, and he had got prosecuted and he's in jail now last year. So sometimes you're a hero, sometimes you're a villain. I don't know what to tell you there. That day he was a hero. Later on he was a villain. Apparently he wasn't doing it at that time period. I don't know. Maybe it was a multi-millions lawsuit. It could be that he was like, I'm making shit and I did these big things. What the hell? But who knows what happened there. Anyways, so chromium 6 plus, it's up on the top of the periodic table, so it can achieve 6 plus oxidation states. You go lower in the periodic table, you don't achieve 6 plus oxidation states. Okay? It's incredibly difficult to do because of this energy lowering effect right here. Okay? All right. We okay with that? Okay. I got off on Aaron Brockovich, but I guess